Okay, this video is going to be a demonstration of the analog input capabilities of the SLIC 500 processor, specifically for the NI4 card, which we have in the lab. The diagram that I have here is a depiction of the standard wiring boards that we have in the lab. We have the local rack here with the power supply, the processor, and the I/O cards. Here we have the last card in slot 3 is our analog input card. I have a simple circuit set up here with two 6-volt batteries, which supplies the first input on the card in slot 3 for our analog input. I have a plus and minus supply set up here. The bridge between the common point between the two batteries is a reference point, and then I have a potentiometer here set up so that I pick off either plus 6 volts or minus 6 volts depending upon the position of the potentiometer. So the way this is set up, if I turn the potentiometer all the way clockwise, I get plus 6 volts on the analog input. If I turn it all the way counterclockwise, I get minus 6 volts, and if I put it approximately mid-range, I should have 0 volts. So that's my circuit here. The card should be set up for 10 volts plus and minus, and as we know, it's an integer word, 16-bit integer word, so the value of counts obtained from the card will range from 32,767 to minus 32,768. So plus 10 volts will give me 32,767, minus 10 volts will give me minus 32,768. So that's it for the diagram. Well, I'm going to go to RSLogix here, where I have a simple circuit set up, simple move statement. If I go to the I/O configuration, I'll just verify that I have my I/O set up, and in card slot 3 I do indeed have the analog 4-channel input NI4 card, and as we know this can be set up for current or voltage, we will assume that this is set up for voltage so that 10 volts is equal to our 32,767. So I have a move statement here, a very simple move statement, where I have the input word, and I'm storing that in a destination of F80. It might be a little bit unusual that I would use a floating point number to store an integer value, but I'm going to do some calculations on this F8 number, so I'm going to need a floating point number in that position. So I'm going to continue with the F8 data files. So a little bit more needs to be said about the source here in our move statement. If I open up the input data table, I can see the bits for card 1 from 0 through 7, the 8 bits representing the inputs. But I also have values for the results from card slot 3. I have 4 results here, and this is not in a form that I can use readily. I should make a very specific point here. The data address here is very important. It is I:3.0. You will notice there is no backslash, so there is no bit delimiter. This is an actual word. This is an entire 16-bit word. So the value returned here is the result, a 16-bit word, a result of all of these bits. So in order to read that value, I'm going to change the radix here to decimal. And now I have a decimal number, and I can put any number in here that I want. I can put in 550, something like that. At any rate, I can put any number that I want from 32,767 plus and minus. So I've got a value in there. In the lab, we're going to simulate adjusting the potentiometer, so we're going to adjust this number up and down, plus and minus. So I'm going to just leave that at that. I'm going to verify my project. There are no errors. I'm going to download, and then we will just make a simple demonstration Better go into run mode here first, huh? And we will make a simple demonstration of just changing the number. If I go to 32,767, we'll see that the number changes, my move statement changes. I can go to minus 32,768, and that changes, so my move statement works appropriately. Based on a 6-volt input and doing the math, I would return, for if I had the potentiometer adjusted fully clockwise, I would return a count approximately 19660. So I'm going to leave that one there. That's simulating that the potentiometer is turned fully clockwise and I'm getting exactly 6 volts return. So I'm gonna leave this now, and I'm going to insert a rung here, because this raw value is just a raw value of counts representing the 0 to 10 or minus 10 to plus 10 volts. So I'm going to add a scale factor here, and I'm going to do that by using a divide instruction, where I'm going to take the raw value and divide it by 3276.7, and I'm going to store that in F81. I've already had this instruction described before, so it comes out as a scaled analog input value. So I'm going to take the value of counts, which is the maximum can be 32,767. I'm going to divide it by a scale factor of 3276.7, and I should get 10, exactly 10, when the counts up here are 32,767, and also similarly in the negative direction. So I'm going to verify the project here. Everything looks good. I'm going to download this, and yes, we're going to do all this stuff, and I'm going to go into run. And now you can see, with the value that I had put in there from the start, which I said should represent 6 volts, account 19660, I'm returning a value on F81 of 5.999939. So that's as close to 6 as I'm gonna want it to be. I'm pretty happy with that. So our scaling factor appears to have worked properly. So I can dummy some numbers in here, and if I wanted to check 32,767, if I put that in, that would be maximum. It wouldn't be capable in the circuit that I have, because I just have 6-volt batteries. But if I had 10 volts and I had exactly full 10 volts on the input, you can see my scale value is correct for 10 volts. If I put in minus 32,768, then we see I get a minus 10 volts back. And of course, obviously if I put in 0, I'll get 0. If I put in minus 19660, so the potentiometer is fully counterclockwise, I get a return on F81 of minus 6, and that's exactly what I should get. So that's the demonstration of analog input circuit in SLC 500, and that concludes this video.